Now let's explore the deep learning workflow with a computer vision application. Let's learn a little bit about deep learning. So deep learning is a key technology driving the current artificial intelligence megatrend. Its origin dates back to the very early computer applications that evolved to include machine learning, which it's now considered a subset of. So machine learning is a statistical method that enables machines to learn tasks from data without explicit programming. And deep learning is a subset of machine learning using neural networks with many layers that learn representations and tasks directly from data. You may have also heard of some other mainstream applications of deep learning, but how many of them would you consider applicable to the engineering and science domains? One such example is the deep learning object detection, which is where a trained deep learning detector will scan an image or video frame to certain objects. It will not only find the objects in the image, but will draw a bounding box around it. Like you see in the image on the left side. You have the bounding box around the dog, the bicycle, and the car, and they're also overlapping. The same technique is being used by Shell to locate text that identify different machinery on location. By automating this process, allows Shell to perform more efficient maintenance on their equipment. So let's compare traditional machine learning and deep learning. Machine learning is teaching a computer to do something by giving it features to look for. In this case, we want computers to recognize a car. So I have to explicitly define the features of a car. For example, the headlights, the windows, doors, tires, etc. Deep learning is end-to-end machine learning. It determines the appropriate features and does the classification on its own. In this case, I give the computer 1,000 pictures of cars. The computer extracts the appropriate features and can classify a new image as a car. More data is equal to better classification ability. This idea of automate feature extraction is made possible by a neural network architecture. A neural network consists of many layers. We start with an input layer, which would be pixel values for image of a car. Then we have a series of hidden layers, which each perform different tasks for determining the characteristics of the car. And finally, we have an output layer, which can perform classification. Our data that we use to train the network gets propagated through these layers to create a model for our data. Let's get into the specifics of what the process involves. When I talk about creator detection workflow, a simple view results in three main stages: data preparation, algorithm and modeling, and deployment. This is an iterative process. Once you deploy your system, you get more data, you iterate back and refine and tune your model and so on. So through this talk, I will go through parts of the workflow. I will talk about some of the challenges within each part and point out how Matlab can make it all come together efficiently and effectively to deliver value to you. The application in this example is a deep learning model to detect craters on the moon's surface. The motivation of this application is about spacecraft moving towards autonomous operations on space exploration. The distance from Earth makes real-time ground control impractical. They could also help pinpoint safe landing locations from craft. Data preparation and management turns out to be one of the most critical ingredients to success. And it's really, really hard. Today, data comes from multiple sensors and databases, structured and structured format from different domains. And if data doesn't exist, We need to create synthetic data and so forth. Data labeling is required for any kind of supervised learning algorithm. And this can also not only be time consuming, but also prone to errors. Specifically, we are going to discuss the two most common questions when it comes to data preparation. How do I access large data that doesn't fit in memory? And how do I label my data? So for the first question, when training deep neural networks, we are working with really large amount of data. So often we cannot load all into memory. One way Matlab handles this problem is with data stores. Rather than loading all your data into memory, data stores load in data only as you need it. They act as a pointer to the data. Matlab has data store capabilities for images, large images, and data files. Another feature that addresses the big data issue is tall arrays. Tall arrays allow you to work with out-of-memory numeric data. In the deep learning space, you can use this when training deep neural networks for numeric arrays. And the last feature here is big image. It's used to read a large image file and the image data it contains. So a big image object represents really big images as smaller blocks of data that can be independently loaded and processed. For example, this is very, very large dimensions, as you can see in the slide, and you can divide this image in small blocks and bring each image for pre-processing. So for the second question, how do I label my data faster? Labeling data is one of the most tedious and time-consuming part of deep learning in general, because it's a lot of data. Imagine manually drawing bounding boxes around thousands of images, or having to define the classes of every single pixel in these images. And literally, I have not seen engineers saying that I love to label my data, but this is absolutely necessary. Let's see how Matlab makes it easy to do these tests, or at least easier to do it. Here we have the image and video labeler. So for the image labeler, you can automate the process of labeling by selecting image processing tasks to find the features in the image. In this case, we want to automate the process to detect vehicles in the image. So you can, if the algorithm doesn't work 100%, you can manually go there and also mark the region of interest for the car. Also, if you want to do some pixel-based segmentation, you can also select different classes of the objects by segmenting the pixels: cars, buildings, trees, pedestrian. This is going to be the input for training for a image segmentation algorithm. So the output is what is in the image. You have every region of the image in a class. Now let's see the video labeler. So you can call video labeler app by typing the command in Matlab, or you can go to the apps tab and open video labeler. Here you bring the video. You can create a label of the object you want to find in the video. So here we see a video of the craters in the moon. So we want to create a label for crater. So we can select the part of the video that contains the object. And manually you can go and mark the craters. You can stop and mark additional objects. You can export. Now let's move on to the second step in the workflow, the one that perhaps gets most attention, AI-based algorithm model. Now let's explore the Deep Network Designer app in Matlab, so where you can drag the layers you want to create in your network. As you can see, you're connecting an input layer with a convolution layer. You can add also a fully connected layer. If you already have your network in your workspace, you also can import it directly to Matlab and do some adjustments there. And also you have the deep learning network analyzer that you can analyze and check if your network is correct. Within the Matlab environment, you can build different vision-based deep learning algorithms, such as for classification, object detection, or semantic segmentation. While working with classification, you can build your own model, or also you have access to many pre-trained models. On object detection side, you can build models such as YOLO v2, v3, SSD, and many more. Similarly, while working with semantic segmentation models, you have access to frameworks like SegNet, UNet, DeepLearn v3. Our focus today is object detection using deep learning, where we will use the YOLO v2 network architecture. Object detection systems are ideal for applications like autonomous robots or scene monitoring. Here is an example of an object detection system that identifies craters on the surface of the moon. There are many algorithms that make this possible. Some of the prominent ones are YOLOs in RCNNs. So what is YOLO? YOLO means you only look once. It's a single neural network evaluation applied to a full image for prediction, and unlike RCNNs that perform thousands of evaluations on a single image. So how it works? YOLO object detection network mainly contain a feature extraction network and an object detection network. Feature extraction network, typically a ResNet, a VGGs, or inception models, choose a layer as a feature extractor and truncate the rest of the network with an object detection network. So it contains less layers than feature extraction network and contains a YOLO-specific layer with anchor boxes. For building a YOLO v2 based object detector, there are steps we need to take care. Load data and explore, create YOLO v2 object detector, and train and test the detector. Let's go inside Matlab to load, explore, and visualize the data. I have opened a crater detection YOLO v2 live script file. Once the data is labeled, I can import the data directly inside the workspace or load it from the store file. Let's go inside the directory to see how data for this application looks like. So I see I have numerous images that I have relabeled using Video Labeler app. Now I want to visualize and verify the annotations. So for that, I can apply use insert object annotation function to overlay bounding boxes and labels for this frame onto the image. Now, the second part, which is most important, is building the YOLO V2 network architecture. As we have seen before, YOLO V2 consists in two parts, feature extraction part and detection part. The steps involved in this process will be importing access and feature extraction network. This is identifying the layer to be used for feature extraction and removing all the layers after that. The third step will be to create a YOLO V2 detection subnetwork. Finally, connect the detection network with the feature extraction part. To build a YOLO V2 network, I will invoke Deep Learning Designer app, which allows me to import network from different supported pre-trained networks in Matlab. So here I'm going to use the ResNet 50. Once imported, I have identified the layer to be used for feature extraction, which is in the case I choose to be the layer 140. And next is to remove all the layers below that. The third step now would be to build the detection subnetwork, which may involve some convolution, batch normalization, and ReLU layers, followed by a YOLO specific layers, like YOLO transform layer and YOLO output layer. We can define the properties of individual layers in the right panel. Last step will be to establish the connection between the feature extractor and detection subnetwork. Once the network architecture is built, you can validate the network by analyzing the network for any errors from within the app. Once done, you can export the network for training. Final step will be to train and test the detector. For training the network, you can use training options functions to define the optimizer mini batch size or learning rate. Once you're done with training settings, you can use a train YOLO V2 object detector for training the network. Once training is complete, you can evaluate the network for precision. Here I am creating using an image for data store using files from a table and box label data store using the labels column from table. Function detect will give the result on the images using the train detector, and then they evaluate detection precision and using the results to validate it against the ground truth data. Deep learning models have to be incorporated into larger systems to be useful. For deployment, we've got a unique code generation framework that allows models or entire applications developed in Matlab to be deployed to embedded devices or enterprise systems, cloud services. Matlab enables you to deploy your deep learning applications from a single source in Matlab to various embedded hardware platforms such as NVIDIA GPUs, Intel and ARM CPUs, Xilinx and Intel SOCs and FPGAs. With the help of MathWorks tools, you can explore and target embedded hardware easily. Matlab can generate native, optimized code for multiple frameworks. It gives you the flexibility to deploy it to lightweight, low-power embedded devices, such as those we use in cars, low-cost, rapid prototyping boards, such as Raspberry Pi, edge-based IoT applications, such as a sensor and controller on a machine in a factory. Now, the final part of the entire workflow is code generation and deployment. For code generation, I have written a small function, YOLO V2 detect, which is importing a pre-trained model, running inference on the image to provide bounding boxes, and then plotting those bounding boxes back to the image using insert object annotation to visualize the results. For code generation, you can either do it from command prompt using code gen function, or you can invoke GPU Coder app for the same. In the GPU Coder app, you will need to first give the function for which you want to do the code generation. In our case, it will be the YOLO V2 detect. Hit next. Now since you are doing code generation for embedded target or C++, you will need to have defined the inputs. You can choose to just provide the input types, or you can write a test script like this, which you can then pass it automatically identify the input types. Once this is done, next you can check the code for code generation readiness. This will check for any unsupported functions or memory leakage. After this, you need to provide the setting for code generation, such as types of code you want to generate. GPU Coder gives options to generate plain, simple C++, CUDA coder, or you can generate statistic or dynamic libraries. Also, you can choose NVIDIA GPUs, which libraries you want to target. Here I'm choosing CUDA at DNN, but you can choose from Tensor or CUDA DNN. Once the entire setting is done, you can go ahead and hit the generate code. And the generate code is highly optimized for C++ and CUDA, capable of leveraging NVIDIA target board specific libraries like cuBLAS, FFT, and deep learning specific libraries such as CUDA, MN, and TensorFlow-RT. Also, it takes care of optimizing memory management and data transfer from host to target. So the generated code is fully accessible to you with no dependency on Matlab. I can also find max files in my directory, which is generated and tested. I can go inside the script test and try the YOLO V2 detect max and see the generated code behaving exactly similar to Matlab code. The generated max will give faster inference as compared to original Matlab implementation, since it's highly optimized C. This old CUDA code leverages target specific libraries. This completes our 3 steps workflow.